I'm Nairi Woods, and I'm Dean of the Blavatnik School of Government at Oxford University. The Kyoto Prize was founded by Dr. Kazuo Inamori in Japan to celebrate the very best international achievements in science, in the arts and philosophy, and in technology. The prize is run by the Inamori Foundation and is held and celebrated in Kyoto every year, as well as here in Oxford. The award reflects Dr. Inamori's vision of a harmony between science and civilization and the enrichment of the human spirit. Sadly, we lost Dr. Inamori in 2022, but we're delighted to continue celebrating his vision with the Kyoto Prize here in Oxford each year. The Kyoto Prize celebrates the kinds of human achievements that humans can only achieve when they live in well-governed societies. And that's why here at the School of Government, we celebrate these brilliant scientists, technologists, people working in the fields of the arts and philosophy. These are things that well-governed societies permit human beings to do with excellence. The previous Kyoto Prize winners are a who's who of brilliant minds and human beings across the world. Primatologist Jane Goodall, the linguistics professor Noam Chomsky, the philosopher Bruno Latour, and this year we'll be celebrating 3 more. The Blavatnik School here at Oxford University is a school with a mission to support governments to improve and to make more flourishing communities for people across the world. The school does this by teaching, through research, which is very applied and takes place alongside governments, and by engagement, by bringing people with very different points of view together and building unlikely coalitions to support human flourishing around the world. It's our great delight to have this collaboration with the Inamori Foundation and the Kyoto Prize, which celebrates the same kind of values, the humility and commitment to serving humankind all over the world. Well, good afternoon, and a very big welcome to all those of you who have been with us through this Kyoto Prize set of lectures, and to the newcomers here today, colleagues from across Oxford, as well as students from St Edward's School and from Cheney. So delighted to have you here with us, and from Cherwell. You're very welcome, and I hope you'll keep coming back to the Blavatnik School of Government. We are delighted to have here with us today Mrs. Inamori Kanazawa and the team from the Inamori Foundation, who have continued these prizes and who join us every year. This is our 8th Kyoto Prize lecture series here at Oxford. And this afternoon we are celebrating and hearing from Dr. Paul Hoffman, the 2024 Kyoto Prize laureate in basic sciences. And before I welcome Paul to the stage, I'd just like to thank in advance Professor Ros Rickaby, an Oxford colleague, who is Chair of Geology in Oxford Earth Sciences Department. Thank you, Ros, for joining us to lead the Q&A, which will come immediately after the lecture. When the lecture is finished, I'd like to just invite you all to join us for drinks and conversation up on the 4th floor terrace of the school. But thank you all for joining us, and there is nobody better to introduce Paul Hoffman than Paul himself in the short video that will precede him coming onto stage. Thank you for being with us.
Many field geologists, they get fixated on the details and the observations and the facts. But I love ideas. I love big ideas. And I love testing them. So I like the details, but I also like the big ideas. Geological mapping is like the anatomy of the Earth's skin. Okay, and you can tell a lot about the lifetime of a person from studying their skin. Biologically, we evolved to be hunter-gatherers. To be able to combine your biological makeup with our great cultural thing called science, to me, was the best of both worlds. If you have a problem, the first thing you should do is take 2 steps backward, okay? Because very often when you don't understand something, it's not because you don't have enough detail, it's because you're lacking the broader context. It's an honor and a great pleasure to talk to you here at the Blavatnik School of Government, because it's no exaggeration to say that my existence in science is due to a government agency. The Geological Survey of Canada was founded in 1843, 24 years before the Confederation of Canada itself, and its mandate was, past tense, to make geological maps and synthesis of the bedrock and the superficial deposits of the vast landscape that is our nation, for the dual purpose of attracting and facilitating natural resource exploitation by the private sector, and to provide information for policymakers in government. The Geological Survey of Canada hired me and many other students as apprentices to active field geologists on field geological work, which not only complemented what I learned at university and the classroom, but paid me a salary through which I could fund myself through university debt-free. Because I showed some talent, the survey totally funded my thesis project, in addition to the salary. And after I had taught for a year, they hired me as a full-time research scientist, the best job I ever had. I grew up in the city of Toronto, about 1 million people at that time, but my parents had property in the Caledon Hills outside the country where they built a 2-room cabin, which to this day has no electricity, running water, or telephone. And we lived there every summer when we weren't on camping trips, and every weekend throughout the year. My parents believed that young children should be kept out of doors and unsupervised as much as possible. This photograph was showing my mother, who was a primary school art teacher, and taken by my father, who is an industrial paint chemist, neither having more than high school education, but a house full of books. Made this picture by my father that is clearly staged. My mother did read to me, but only after sunset. During the daytime, we were kept out of doors, and I spent a lot of time in the city or the country just wandering on my own, arguing with myself. Little did I know that I was honing my temperament for a life in science, arguing with yourself. Thanks to the Royal Ontario Museum, I was introduced to geology through mineral collecting, and I became an avid mineral collector as a teenager. It was my one taste of commerce. We collected rare earth minerals on the weekend and sold them to collectors or to Ward's Natural Science Establishment, which then sold to collectors. Rare earth minerals are not rare. It's just they're very small deposits that are not economic to mine with modern large-scale mining technology. They would become economic if we rescinded the child labor laws. At the end of my first year in university, or just before the end, I went up to the professor and said, "Are there any summer jobs in geology?" And he said, "Yeah, you go to Parliament buildings and ask to see Jet Thompson, who is the director of the Ontario Geological Survey. And so that's what I did. And Jet Thompson looked me up and down like it's every day of the week that he talked to freshman students, the director of the survey, who were looking for a summer job. And he said, "Have you ever been in a canoe?" And fortunately, my parents owned a canoe, so I knew how to work a paddle. And he said, "You'll do. Buy a ticket to Sioux Lookout, leaving the 10th of May and returning on the 20th of September." And we spent 4.5 months in the paddle canoe and plowing through the bush, playing the game of geological mapping, which involves predicting in advance the next outcrop. As you paddle around the lake or as you plow through the bush, you try to predict what the outcrop will be. Predicting meaning what kind of rock it will be, what its age and spatial relationship is to the other rocks in which it's in contact with, and through which you work out the structure and the geological history of the region, and from which you base your prediction. And of course, you quickly learn that the most important outcrops are the ones that aren't what you predict they're going to be. This is called the active science, hypothesis testing. Except in field mapping, you're doing synthesis and hypothesis and prediction and test in real time, in the time it takes to paddle or walk from one rock to the next. Now, the problems you're trying to solve may not be very important. That comes down to a matter of picking good problems. During my thesis, I got fascinated by these strange structures. They're called stromatolites, and they're laminated buildup, and these are about 1.9 billion years old. And they're believed to be constructed by microbial mats made of cyanobacteria and other mats. And microbial mats are a fascinating system. They have the politics all worked out. The producers are on top, and the consumers are at the bottom. And because of the beautiful exposures we have on the east arm of Tucho, Great Slave Lake, you see broad expanses of these structures in plan view, in the synoptic view that they would look like if you were there at the time they were growing. You can almost imagine the tide is coming in. Oops. Does this thing work at all? There we go. Ooh. Maybe if I hold my hand the right way, it'll work better. So, of course, I was delighted when I took a year off to look at modern algal mat-built structures in many different parts of the world, the Persian Gulf and Shark Bay in Western Australia, the Bahamas. And here in this hypersaline lagoon are stromatolites built by microbial mats that are just like the Precambrian ones. And it was very nice to know that from the Precambrian structures you could tell the orientation of the shoreline and which was offshore and which was onshore, which might seem trivial, but when you're dealing with folded rocks and you don't really know, but you want to know the configuration of the sedimentary basin, those are rather useful things to know. But I decided not to be a specialist in stromatolites for the rest of my life. Oh yes, what makes a Hamlin Pool in Shark Bay special is the salinity, because the salinity excludes the little animals that like to eat the microbial mats and prevent the mats from growing in the lower part of the intertidal zone. In most modern areas, these snails. Now, I went to university between 1980 and 1987, which is precisely the period of the plate tectonic revolution in the earth sciences, which showed that the mid-ocean ridges are areas where the seafloor is spreading. Mid-Atlantic ridge, the East Pacific rise, and the Atlantic Ocean and the Indian Ocean and the Southern Ocean are all growing in size, whereas the Pacific Ocean is contracting because the floor of the ocean is sinking into the deep sea trenches which line the margins of the Pacific in the northwestern and southeastern parts of the Pacific Basin. And these trenches are places where the dense, cold floor of the ocean, the skin of the ocean, the lithospheric slabs are sinking back down into the mantle because of their negative buoyancy, because they're cold. And when they sink in an area and they keep on sinking in that same area, the mantle into which they're sinking gets colder and denser and starts to sink. And there's a feedback because, of course, the surface part is being drawn towards the sinking area, and there's attraction. And so like leaves above a gutter, there's a tendency of the continents to coalesce over the maximum sinking area. And the implications of this will become apparent. Now, in my day, the textbooks didn't know about plate tectonics. The textbooks mostly said that continents and oceans were primordial, and that continents have mountains along their margins, because of stresses at the interface between the continental areas, the continental crust, and the oceanic crust as the Earth cooled and contracted. Now, this idea became a good deal less attractive when it turned out the Earth was billions of years, not hundreds of millions or tens of millions of years old. Furthermore, this idea spawned in America and does not work very well in Eurasia, where the major mountain ranges like the Urals, the Verkhoyansk, the Chinling, the Himalayas, the Makran, the European Alps are in the interior of the continent, not in the continental margins at all. And of course, plate tectonics provided the explanation for this. Eurasia is a composite. It's a composite of many different continents, each with their own individual history, which came together at different times, bringing their structure and history with them into this greater amalgamation, very, very much like human populations. And the internal structure is like the genetic makeup of a group of organisms, because it's encoded with the history of that bit of continental crust through successions of aggregations and disaggregations. Because what happens when you bring a whole bunch of continents together is that you can no longer have any oceanic material to sink down and cool the mantle. Okay, so you've removed the cold sinkers, and also you've put a blanket over the top, which is the radioactive continental crust. And so slowly that downwelling is converted into an upwelling. Okay, and that upwelling lifts and produces potential energy of the supercontinent and weakens it thermally, and ultimately that supercontinent breaks up and is dispersed and tends to coalesce around the maximum downwelling area, which is often around 90 degrees in arc away from the previous supercontinent. And so as a result of this, there has been a succession of supercontinents, but this is something, I'm getting a little bit ahead of my story, because looking at it as an individual, knowing about a previous, a Phanerozoic, about 300 million-year-old supercontinent called Pangea, first conceived by the German atmospheric scientist Alfred Wegener, that's all of the existing continents coalesced into a single supercontinent, or Pangea. And the idea that Eurasia is a composite got me to ask the question, well, what about this big pink blob that underlies most of Canada, and which is called the Canadian Precambrian Shield, and most of which consists of rocks that are on the order of 1.5 to 2.5 billion, even 3 billion years in age. And so my thesis area, which was in the, if we can see it here, in the east arm of what's popularly known as Great Slave Lake, and we seem to have lost the pointer now. Anyway, it's up in the northwest there, indicated to me the possibility of an ancient, about 2 billion-year-old continental margin right up in the northwestern corner of that big pink area, about 1,000 kilometers inboard of the modern continental margin. And so I decided to mount a long-term mapping project to see what was there. And as recently as about 5 years, 8 years before I started my work, most of this area was unmapped. Between the time this map was published and my own work, there was a helicopter reconnaissance which gave a pretty good idea of where the basic rock types were, where there was granite, where there was metamorphosed sediment, where there was volcanic, but nothing about the age, or either absolutely or relative, and so nothing about the history. But what I knew from the old maps is that up in the northeastern corner, there are sedimentary rocks that seem to be, from descriptions, well preserved. And down in the southwest around Great Bear Lake, there are some well-known mineral deposits that are hosted by volcanic rocks. And so the deal would be that myself and 3 students would go out and we'd work in a specific camp for 2 or 3 weeks, covering as far, large an area, mapping as we could, using boats and walking. So we got used to, walking 20 miles a day or so, mapping as we went along. And every 2 or 3 weeks, the plane would come in with supplies and move us to a new camp, and then we'd do the same thing over again. And of course, we would plan very carefully in advance, from aerial photographs and whatnot, where the best places to put camps, and the overall strategy for how to go about mapping from the standpoint of what we knew about the structure. And so we would start, as soon as the rocks would appear from the snow. This is a picture sort of mid-June at about 64 degrees latitude, so the lakes are still partially ice covered. And as the ice disappeared, this just amazing continental margin folded up appeared. A total continental shelf, slope, steep slope, ramp, all folded up with beautiful sections, nice orbital scale cycles. And, this is as well preserved a continental margin as you see almost of any age. And we were able to date accurately the duration of the passive margin, that is from when the rifted continents first broke apart until it ran into a subduction zone, and it's 132 million years, which is indistinguishable from much, much younger continental margins of similar type. A little bit more magmatism in a number of different environments because the mantle is somewhat hotter at that time. Over in the Great Barrier Area, they're just magnificent volcanic rocks, entire stratovolcanoes, all tipped up on edge, exposed in cross-section, including their internal plumbing and whatnot, because the whole volcanic arc succession is all folded up. Now, it probably doesn't surprise you that a guy is used to, gets a charge out of walking 20 miles every day in the bush, runs 80 miles every week in the off season. But the interesting thing is that my part-time activity in running had unforeseen dividends to my science. The first thing was that when I ran the Boston Marathon for the first time as a 23-year-old, finished 9th in 2:28, there was an old guy named John Kelly, John A. Kelly, and he was almost 60, and he ran under 3 hours, right? I knew hardly any geologist of any age who could run a 3-hour marathon. And the thing about being in field geology is that the experience is cumulative. And so you just get better and better over your lifespan but in my day, most field geologists were, giving it up in early mid-50s. And this was telling me you could go full steam till you're 60. I did my last field season at 82. I'm not a field geologist anymore. I don't want to be a bad field geologist. I just don't have the sense of balance. But, that was the first dividend. The second thing was how to treat and develop a team of students, okay? The students can do way more than they can imagine, but they have to be built up to it with care, with loving care, with both technical and emotional support. They need the gradualism and the support and the encouragement, exactly the same thing that a good coach does with young athletes. I was thinking, while I'm here, everybody knows about Roger Bannister, right? But the real thing is, the secret behind Roger Bannister and his equally talented colleagues, Chris Chataway and Chris Brasher, was his Austrian coach, Franz Stampfel. Okay, so remember that. And let's have a word about Franz Stampfel. And so that's something I learned from sports and having good coaches, is how to train and develop my student assistants, because I wanted to have them able to do work independently on a daily basis as soon as possible. Okay, I would get more of it if we could have more people working, and they would learn way more. Okay, as the 19th century Russian geographer and political activist Peter Kropotkin said, there's no better incentive for research than there's no better incentive for intellectual development than independent research. Okay. So that's, and then the most unexpected of all is that throughout my career, and still to the present, virtually all of my scientific ideas and my occasional witty titles for papers came to me when I was out running, thinking about nothing. And these ideas would just pop into my head. It's the damnedest thing. I used to say running is good for the brain, and people laughed. But then I noticed that so many of my colleagues were taking up running. I knew exactly what was going on. He's not so smart. It's got to be the running. Okay, so this is a very generalization of the map we came up with. Here's the, oh, sorry. Back. Oop, forward. Yeah. So here's the, so here's the continental margin. That's the change from light blue to dark blue is the edge of the continental shelf. The green is the volcanic arc it ran into as a result of subduction out to the west. Okay, and the collisional granites are in the red. And then as soon as you had the arc collision, you had a flip of the subduction polarities, like Dan McKenzie said, and shifted to an outboard position. So you now have an Andean-type situation with the subduction zone dipping beneath the continental margin. And this is the big continental margin arc that developed subsequently with the uranium deposits of Port Radium and et cetera. So, it's just a beautiful exposed example of, it could be a continental margin of almost any age, and which its sense was a kind of a disappointment, because I was expecting this older stuff would be quite a bit different. And it wasn't the most interesting result, actually, that plate tectonics, 2 billion years ago turned out to be so similar today, because I always tell students that the only reason to study very old rocks is to learn things you couldn't learn from studying younger rocks. Okay? However, it must be said that the longer-term perspective, gives a view. So here's Taiwan. Here's the same, continental margin flip in polarity. So this is a collision. It's going on in Taiwan today, which is an extension of the Luzon arc of the Philippines, okay, as a result of east-dipping subduction of the South China Sea. But the buoyant continental crust of the Eurasian South China margin won't go down, so the slab here breaks off. The mountains of Taiwan are the collision zone, so there's no doubt geologically that Taiwan's going back to the mainland. And then because the convergence between the Philippine Sea Plate and the Eurasian Plate is continuing, because this is just a point, and so to take up the convergence, the subduction flips into the weakest spot, and you have a new arc here that goes all the way up into Japan, the Ryukyu arc. And that accretion of this arc progressively in a southward direction with time takes about 2.5 million years for the entire collision and polarity flip to occur. So as a result of the success on this ancient continental margin, I was tasked with making a synthesis of the Precambrian geology of North America in terms of plate tectonics. And what I call the United Plates of America, not such a popular title anymore, unfortunately. But as you can see, it also turned out to be a composite, just like Eurasia. And many different previously independent continents, very, very much generalized here, which aggregated around the red one, the Ray province. That was the keystone that everything else sort of packed in around. The oldest collisions are adjacent to the Ray, and so it built outward from there. And it built outwards globally, and so there's an entire supercontinent that built at that time. And you can track the coming together of, say, 3 of the major blocks within the Canadian Shield from paleomagnetic data. Paleomagnetic data is a bit awkward because paleomagnetic data gives you the latitude and the declination, the direction to north, but it's blind to longitude. You don't know where the longitude is. So it's awkward to portray where the continents are. It's easier to portray the migration of the pole position under the fixed modern geography. So the red, green, and blue colors track the poles as the continents are converging. So what you can see here is that the red and the green first meet, and then they travel together and then meet the blue, which is this one down here, sometime later. And that's exactly the order of the collisions that you can tell from geochronology on the ground. So it's nice to have this independent support from paleomagnetic data. So here's the most recent supercontinent, the Pangea of Wegener. And so what we now know is that there's been a succession of supercontinents, and that's something we could never have learned from just looking at the last, half billion years of Earth history. So the first one may have been, this is somewhat more speculative, Kenora, around 2.7 or so. And this is the one in which North America was the core that I called Nuna. Nuna is the Inuit name for land, meaning any land south of the Arctic Ocean, which is, when you think about it, all the land there is. So I thought it was a good name for a supercontinent. And Rodinia, which comes from the Russia, rodit, which means to beget. So this is the supercontinent when it broke up, gave the modern continents. And then Pangea, which it has sort of a double peak. So these are zircon frequency peaks. Zircon is a minor constituent of most granitic rocks, which is special because it can be dated very, very accurately by uranium-lead geochronology. Now, what about the next supercontinent? If we look down, we can see what's going on, I think, best if we look down at the world from a northern polar perspective. Okay, so imagine that Eurasia and Africa are fixed. Okay, and so what's happening is the Atlantic Ocean is opening, the Indian and Southern Ocean are opening, and so Australia is moving northwards towards Eastern Asia, and the Americas are pivoting toward the right, okay, just like American politics. Okay, it's pivoting, clockwise to the right, and the Pacific is the ocean basin, the only ocean that's closing. And so, inevitably, I think as a result, the Americas are going to close right around, and we're going to have the next supercontinent, which I called Amasia. And this is an Australian perspective, so Australia is tucked in there like a joey in a pouch. And then everything changed. The Conservatives came in with a massive majority in 1984 in the Canadian Parliament. And over the next 2 or 3 years, the survey was completely defunded. It was a little bit more humane than what's going on in America at present. We weren't fired, but there was no more budget for operations. And so the ambitious people, of course, it was, the best job in the world can come to an end. I never really wanted to teach. I wanted to do geology. I wanted to teach geology. And I loved having students in the field as apprentices. I wasn't so sure about classroom situation, but anyway, and I put up a bit of resistance. So in the end, I left the survey the same way I arrived, fired with enthusiasm. Not my quote, that's John Kenneth Galbraith, a Canadian economist at Harvard. Now, in any case, I was thinking about life after tectonics. I thought that tectonics was, starting to get a little old, and so I was looking for new things. In 1989, the first Greenland ice cores were published. And so there's two depictions of the same core. On the left is the true depth scale. Oops. I much prefer to have the pointer in different hands, but let's see what we can do here. Okay, so on the right is an age model, which takes into consideration the deeper parts of the core are much more compacted than the shallower parts of the core. It doesn't really matter. What's on the x-axis is oxygen isotopes on the left and the equivalent inferred temperature on the right. And the thing to see here is that during the Ice Age, okay, which is the blue area, the climate variability is much greater than during the Holocene, the post-Ice Age period. So something about the colder climate was making the climatic variability much larger. Okay, so that was kind of interesting. And so one of the obvious reasons why this would be the case is what's called ice albedo feedback. It's actually only a partially accurate, it's an accurate description, but it's incomplete. It really should be the ice albedo insulation feedback. And the idea is if the ocean was entirely covered by sea ice, 80 to 90% of the incoming solar radiation would be reflected back into space and lost. If the sea ice wasn't there, 80 to 90% of that radiation would be absorbed by the water, which would warm up and radiate and warm the air. But with the sea ice there, you know, most of that is lost. Now, the feedback results from the fact that if it gets colder, you have more sea ice. And so therefore, there's more reflection, which makes it even colder. So there's an additional, you know, positive feedback to the initial change. Okay. And if it was only the albedo thing, you would think that it wouldn't have any effect in the winter, because in 4 months in the Arctic Ocean, it's dark. You know, who cares about albedo when there's no sunlight? It turns out that the presence of sea ice has an even bigger cooling effect in the winter. And the reason is because it shields the air from the warmth of the water. Okay? The air is much colder than the water, but the air can hardly feel the warmth of the water when there's a barrier of sea ice, you know, insulating the air from the water. So it's a very powerful feedback. And in 1969, a pair of papers written by a Russian scientist, Mikhail Budiko, in Leningrad, now St. Petersburg, and William Sellers in Tucson, Arizona, published simple energy balance models of the Earth's climate in one dimension. That is, the surface temperature as a function of latitude from the equator to the pole. Okay, and so of course it gets colder because of the increased angle of the inclination coming in, so a given beam of light falls over a larger area, and so there's less heating, less insulation per unit area. So that's the first thing. But then that's moderated to a degree by poleward heat transport by the circulations of the ocean and the atmosphere. And in these simple models, that was just handled as a simple diffusion. Okay, which isn't exactly accurate because the processes do change by latitude, and that can be done to a degree in more complicated diffusive models, but these were relatively simple. And then the thing that turned out to be really important was the albedo, and particularly the albedo of sea ice, because the ocean is very, very dark and absorbing, but sea ice is very, very, very reflective. And it turned out because of the shape of the Earth, as the ice cap, the polar ice cap, grows incrementally, the area that changes color gets larger and larger. In other words, the feedback gets bigger and bigger. And so there's a tipping point, okay, a bifurcation beyond which the advance of the ice becomes self-sustaining and unstoppable until the ice margins meet at the equator and the ice thickens up because of the back pressure of the ice flowing in from both hemispheres. And the temperatures drop far below the freezing point everywhere, and the ice thickens to hundreds of meters, continually flowing equatorward. Now, the climate physicists who came up with this, and this was very controversial in climate physics and very interesting, because the problem for the climate physics people is that how could it be that the Earth has survived for billions of years and yet this never happened? Because the calculations suggested, and the motivation for doing this work was to see how much can we change the sun or the equivalent greenhouse effect, positive or negative, to get a climate like the last ice age, or like the Pliocene, which is warmer than today and could be something like where we're headed. That was the motivation for doing this work. And what they found was that the tipping point was not very much colder than the last glacial maximum 20,000 years ago. So how could it be that it never actually happened? Because they assumed that if it had happened, it would be permanent. Because to escape from this condition, they found that you needed to heat up the solar input by 25%. And solar variability, you know, on relative short timescales, it's 1/10 of 1%. And yet you need 25%, which is approximately a 1,000-fold increase in carbon dioxide. Okay? So they never thought about talking to a geologist. about this, because they thought it was impossible. Otherwise, nobody'd be here at this lecture. So meanwhile, over in geology, because of this great controversy in the mid-19th century about the origin of the diluvium and much of the landscape of, boreal Europe and North America, geologists got very good at recognizing where glaciers have been, and long after the ice has completely disappeared, right? Geologists have absolutely no doubt that this thing down here, this object that's creating this dam here, was produced by an ice sheet. Even over here, where the slope is too steep to hold any deposit, you can still tell a glacier was there because of the polished and striated bedrock that's there. Anyone here heard about Roche-Moutonnet? Yeah, a few people. So these polished and asymmetric, which show the flow direction of the ice, are commonly called Roche-Moutonnet. And all the textbooks say it was because they look like sheep. And I said to myself, the French, with their love of language and their love of precision, they would never use such a sloppy metaphor, because they don't really look very much like sheep at all. So I did a bit of research. Moutonnet doesn't talk about sheep. It has nothing to do with sheep, or very little to do with sheep. What Moutonnet means, it's an obsolete French word for what French noblemen or their servants did with sticks of lard, the sweeping action to keep their hair pieces properly coiffed, right? That's Moutonnet. You say it's perfect. I mean, 1894, this is an amazing portrayal of the extent of glacial ice at the last glacial maximum. This is not just artistic license down here. This is really accurate, and by T.C. Chamberlain. The only thing that might be a little inaccurate is that passageway between the Cordilleran and the Kuwaitan ice sheet, which is there for the pre-Clovis people to come down, but they probably came down the coast. Okay, so these three climate states, so these models suggested, they came up with some surprising results. One of them is that you could be in either one of these three states with exactly the same radiative forcing. Okay, it all depended on the prehistory. Okay, so there were multiple stable states, and the second thing was, because of this tipping point and this bifurcation, you can't be. This is called the large ice cap instability. You can't be. You can be here or you can be here, but this is not a stable climate. The early models all suggested this is not a stable climate, and there was concern that's where we might be headed, and the Arctic sea ice might rather abruptly disappear. Models that have seasonal cycles of sea ice don't show that bifurcation. Ones that don't have seasonality do. But the large ice cap instability is a very stable feature of virtually all climate models, including complex GCMs. So here's the last 3 billion years. 90% of the last 3 billion years has been non-glacial. That is, no large ice sheets anywhere. That seems to be the default climate state. And then the climate state we're in is the paraglacial state. That's with a few large ice sheets, Antarctica, Greenland, and for most of the last couple of billion years, also Laurentia and Northern Europe. And then the panglacial state, which is about 3.5% of the last 3 billion years, is the so-called snowball. And these are the two that are the best known, that occurred in the Cryogenian period, which the last one ended about 100 million years before the Cambrian explosion. So most life forms have already evolved by this time. Most forms that we're familiar with, of bacteria and archaea, including eukaryotes, have long been in existence at this time. And here's the distribution of the well-established true glacial deposits of these two ages, the Sturtian and the Marinoan. And as you can see, their distribution is pretty much global. And the areas that are absent in these deposits, like eastern North America, for example, are really areas where there are no rocks of cryogenian age. They should not be inferred as areas that were necessarily ice-free. There's just no record. And the deposits themselves are, almost indistinguishable from Quaternary glacial deposits. This is a till or till-lite when it's lithified in northwestern Australia. And glaciers erode by two mechanisms: by abrasion, which makes fine rock powder, and by plucking. the downstream ends of Roche-Moutonnet, you get melting on the upstream and then freeze-on in the downstream. And where you have freeze-on at the base of the ice, you get plucking. It picks out, large blocks of rock. And those blocks of rock get smoothed and rounded by the shearing action of the ice, with the fine powder being the abrasive agent, like emery for a lapidary. And so it's characteristic of glacial deposits that these blocks are rounded and polished. And also where rock has been dragged along the base of an ice over bedrock, it gets faceted, like the lower left there, with scratch and groove marks going in various directions. So these are among the plethora of diagnostic indicators of glacial action, and these are from cryogenian examples. Now, we can restore those same deposits in a paleogeographic map. That's in the continental distribution that we believe existed at the time from existing paleomagnetic data, other paleoclimate indicators, and ancestral relationships between different blocks. The Sturtian at the lower part, the Marinoan in the upper part. You can see Rodinia is in the supercontinent is in the process of breaking up at this time. And what you can see is the red stars, which are the glacial deposits, are basically at all latitudes. Okay. And many of these deposits are associated with thick carbonate successions, which, because of the saturation chemistry of carbonate, must represent the warmest parts of the surface ocean. So here's the saturation state of seawater, and the red is the highly oversaturated, and that's where carbonate production occurs, particularly non-skeletal production, and all Proterozoic carbonate is basically non-skeletal until the last few tens of millions of years, well after the cryogenian. And as you can see, the highly oversaturated states are between about 35 degrees north and south. And if you look at the carbonate-hosted glacial deposits, they have exactly the same distribution. Less than 35 degrees latitude, the warmest parts of the surface ocean, verifying the paleogeography and telling geologists that, look, buddy, you've got ice at sea level in the warmest parts of the global ocean. The colder areas should have been frozen as well. But geologists just didn't know what to make of this, because not a single geologist quotes any of that climate physics literature. They were like in different worlds. Now, I knew a little bit about it because a paleomagnetic friend of mine, Joe Kirschfink, the guy who named Snowball Earth, told me about this idea in 1989. And so when I left the survey, I looked around the world for a place where there were glacial deposits which looked like legit, that were in a thick carbonate succession, in an area that looked good for being able to do a long-term, field project, which means political stability. Namibia in southwestern Africa had just become independent in 1990. I first went there in 1992 and started full-time operations in 93. I was impressed by what the SWAPO government had done after independence, various steps they had made. It seemed a very good chance that, like neighboring Botswana, this would be a stable representative democracy. It's mineral rich, it has an excellent geological survey, aerial photographs, maps, professional colleagues, good university. And so they've been extremely supportive, especially because I was working in the northern part of the country where very little work had been done in the previous decade or two because of the Civil War leading up to independence. And so I used this as both my research area to be completely convinced in my own mind these are real glacial deposits at sea level. There are no large stratigraphic gaps between the carbonates and the glacial deposits, and used it as a training ground for graduate students, which went, set up independent projects all over the world on these deposits, really bearing down on it. And we got a paper published in Science despite 2 negative reviews. And the positive review says this probably should be published even if it's wrong, which is not the strongest recommendation. But Brooks Hansen, the Earth Science editor in Science, somehow got this paper and it got published. And of course, it raised a huge ruckus. But these are small numbers, but nevertheless, it caused a great increase. And what was best about it is the increase in the diversity of the different disciplines that we're studying the problem. Now, the key about Snowball Earth is it has a theory behind it. And because it has a theory behind it, it makes predictions that can be tested with new observations. And the theory stems from this small group of planetary scientists at the University of Michigan in Ann Arbor, Michigan. And the thing, they were in a group of paleobiology working group that was headed by a paleontologist at UCLA named Bill Schupf. And that's where they got to meet this guy, Kirschvink, who told me about this story. And what these guys were most interested in was what's called the dim early sun paradox. Okay, it's widely believed in astronomy that the sun's luminosity has increased by about 30% over solar system history in a broadly linear way. And so the paradox is, how could the Earth have maintained the habitability, allowing life to evolve, if the sun has gotten 30% brighter over geologic time? It seems unreasonable. And what they deduced is that the temperature dependence of silicate weathering, as it's called, which is basically the conversion of rock into soil, which involves chemical reactions which consume carbon dioxide and ultimately deposit it as limestone in the ocean, some chert. The temperature dependence means that the carbon dioxide concentration acts as a thermostat. If CO2 gets too high, the weathering rates spin up, the consumption rate, and it puts a roof on the rise of CO2. Similarly, if the CO2 gets lower and it gets colder, then the rates of CO2 consumption go down, and then that limits the cooling. And the CO2 level automatically self-adjusts over geologic time to whatever level it needs to be to maintain a balance between the outgassing of CO2 by volcanoes and the consumption of CO2 by silicate weathering, to maintain that balance, okay? And that acts as a geothermostat, because that balance can only be maintained if you have an active hydrologic cycle. Now, they wrote this famous paper in 1981 explaining this geothermostat, and in the last page, they say, this geothermostat is probably what prevented the ice disaster that plagues or that afflicts energy balanced climate models. And they quote Boudico and Sellers, right? However, if the global glaciation did occur, and maybe they realized that the ice albedo feedback works on a time scale of months, whereas the silicate weathering feedback operates on a time scale of millions of years. So it wins the war, but it loses the battle. So it can't really police it if the forcing occurs quickly. They say, however, if a global glaciation did occur, the consumption of CO2 would fall nearly to zero, because you would no longer have any liquid precipitation, and it's rainwater that removes CO2 from the atmosphere, not removed very effectively by snow. The ground is frozen, so there's not much soil formation going on. The seafloor weathering is very, very slow because the water is so cold, although it gets a little bit faster as the water becomes more acidic. And so they say within 20 million years, the present rate of outgassing, if there's no uptake, would give you a bar that's entire atmosphere, as heavy as the modern atmosphere, which is mostly nitrogen and oxygen, made just of CO2. In other words, you'd have doubled the atmosphere by adding CO2, about 1,000 times. And that would be enough, more than enough, to melt the ice, and which, because of the ice albedo feedback, the melting would occur very rapidly, predicting, of course, a very hot aftermath, where you have high CO2 combined with a dark surface. And this is the thing that really drew me to the phenomenon, is the fact that there's a theory behind it. And because there's a theory, it makes predictions, and the predictions are that the onset, okay, so this is temperature, and then this is elapsed time. So the onset and the termination should be globally synchronous, the onset at low latitude and the termination at all latitudes, and the duration should be long enough to increase the CO2 concentration by something like 1,000 times, which is going to take many millions to tens of millions of years. We now know there were two events. The first one was at least 4 million, and the second one was almost exactly 56 million, the first one, okay? And so it was this ability to make predictions that really, sold me on that this was a tractable problem. And despite the fact that as recently as 2004, not a single one of these glaciations was directly dated, we now have multiple age constraints from different parts of the world which pin down the onset and the termination of the first snowball to within about 1 or 2 million years in both cases, and the termination of the second snowball to better than 1 million years. Okay, so basically all of these predictions have now turned out to be true, and in fact the Snowball Earth hypothesis has been broadly accepted by geologists who are actively working in this part of the geologic record since 2015, okay, for a good 10 years now. And it speaks highly of the science, actually, because it was highly critical to begin with. I mean, even my friends were they were so embarrassed because they thought I was bringing discredit to the science in addition to just totally spoiling an otherwise, adulatory career. And many aging scientists have fallen into the trap of but the fact that it was testable sold me on it. Okay, so this is the time compared with the last 80 million years. That little blue thing right at the top there, that's the last ice age, about 2.5 million years. The dark blue on the right are the snowball glaciations. And so the blue line, let's see if I can, well, the dashed blue line of the snowballs, this is a phylogenetic tree for bacteria, with the red coloration indicating the fraction of aerobic biomes. Up in the top right there, you can see the time scale for animals and land plants. And for eukaryotes, if you look for the green chloroplasts and orange mitochondria down at the bottom. So as you can see, snowball is very late, but this phylogenetic tree pertains only to the descendants of the survivors of Snowball Earth. Okay? And under the snowball condition, the ice covering the ocean is hundreds of meters thick, and as a result, it flows under its own weight and rapidly closes off any open area or crack that might develop. And so I think that under the snowball condition, the ocean is about 99.9% in permanent darkness for millions of years. And so it doesn't help being a mixotroph when there's nothing to eat. So, and also the ocean temperatures are on the order of -4 to -7 degrees, which is really borderline given that repair of genetic damage is temperature sensitive, gets slower as the water gets colder, whereas the rate of genetic damage is insensitive to temperature. So even under dormancy conditions, you still need to have enough activity to repair genetic damage for an organism to be viable. So actually, I think the ocean is not the place to look for the survivors of Snowball Earth from which we all descended. And I think the way to look at this is to look at what's going on in the modern world. So all field geologists know the range of deer flies, because deer flies are nasty. They bite your scalp, and they have savage mandibles that slash away and make a pool of blood, which they then drink. And so all field geologists know the northern limit of deer flies. And I would say, on anecdotal evidence, that the northern limit of deer flies has migrated about 500 kilometers poleward in my lifetime. Okay? So that's what happens when climate changes. This is in response to global warming. So this is what happens in response to climate change. Biomes move either poleward or equatorward. And if they're moving poleward, then you get extinctions in the polar regions and originations in the tropics. And I think that the same thing went on in Snowball Earth. And the Snowball Earth onset, it takes 200 to 300 million years to go from that tipping point to total ice cover. Long before Snowball Earth, there were mountains that were glaciated. This is Mount Chimborazo, which when Van Humboldt was there in 1802 was thought to be the highest mountain in the world. It's sitting pretty much right on the equator, but the upper 2,000 meters is heavily glaciated. Not far away is Cotopaxi, which is another heavily glaciated Andean volcano. And so I think what happened during Snowball Earth and long before Snowball Earth, microbial organisms, and maybe even some small microscopic ones, inhabited glacial and near glacial environments at the tops of mountains and at least at times in the polar regions. And when Snowball Earth hit, those communities just migrated in step with the ice margins to the equatorial zone of net sublimation on Snowball Earth. And there it is. And it's ice covered, but the ice is dark because the ice is bare, it's sublimating, and so all the dust that is coming off those bare continents accumulates at the surface, absorbs energy, and produces little holes and ponds of meltwater. And so there you have light, water, and nutrients from the dust in combination. Okay, and here's what some of those environments look like. The freshwater environments are living on the glacial surfaces. They're on the left. On glaciers, you get these little cryoclinite holes. The dark patches are dust. They're dark because about 10% of the dust is extracellular sugar that's produced by cyanobacteria and is heavily pigmented to protect the cells from the intense UV radiation. On ice shelf surfaces, which are flat, you get these rolls because of the back pressure, and you get these long linear ponds. The saltwater organisms were mostly in dry valley lakes, like the dry valley lakes of Antarctica, which are covered, which are at net sublimation. The ice caps are thin and clear, so there's lots of photosynthesis underneath the ice, both benthic microbial mats and also high concentrations of plankton, which are concentrated at the very base of the euphotic zone at depths of around 60 meters in Lake Van Den, Antarctica, where the water is warm and nutrient-rich. Okay? And so if you look at these polar alpine habitats, and this is just a list of some of the important ones. We've just looked at cryoclinite holes and deep brines of ice-covered lakes. And if you look at them, because one of the questions is there enough diversity, taxonomic, ecological, genetic diversity to account for the radiation of organisms that we know happened in the Ediacaran and Cambrian and Phanerozoic? Is there enough diversity in these polar alpine habitats? And so I've classified them ecologically according to major parameters: temperature, light intensity, salinity, redox, that's oxygen state, and nutrients, phosphorus or nitrogen. And you can see there are no two of these that are alike. And the cryoclinite holes and the deep brines are almost exactly the opposite in every one of those characteristics. So indeed, there is considerable diversity here, and virtually all the biotic lineages that you need for the Ediacaran and Cambrian explosions, with one or two possible exceptions, can be found in modern polar alpine environments. So I call this the Quito Express hypothesis, because it's a two-way shuttle. Okay, when the ice advances, the people go from Quito down to the coast of Guayaquil, which is on the Pacific coast, about a couple of degrees south of the equator. And then when the snowball is over, they take the train back, but some of the people stay in Guayaquil and restock the oceans. Okay, and all living things descended from the survivors of Snowball Earth. And so that means there's this strange ancestral history that the life we have in the surface biosphere descended from a small subset, a polar alpine subset of all the organisms that evolved before that time, that unusual ancestry should be encoded in the genomes of living organisms. And indeed, we are seeing in a number of different ways that things that would otherwise be very difficult to understand in the molecular phylogenomics of modern organisms make good sense in terms of the snowball events. And I think we're likely to find more and more of these. But geologists are going to have to shout loudly, because it's deeply ingrained in biology that life originated in the tropics, and cold habitats are a late adaptation. And what I would say in terms of the life we have today, not necessarily how life originated, but the derivatives of the life we have today had a very different ancestral relationship. It had a pre-cryogenian history of polar alpine biomes that then survived selectively because those organisms confronted by the Snowball Earth said, wow, this is great, our habitat area is so much bigger. And down at the equator, the cruelty of winter is greatly reduced. And we derive from them. So the Snowball Earth has been the most intense learning experience of my life. And because I've had to jump into the deep end of so many different branches of science that I never had any prior experience with. And every time I do it the same way, I read 2 or 3 good books about the history of that science, from which the terminology and more importantly, the patterns of thinking become sensible and understandable. And otherwise, they're just very strange. And then just jump into the primary literature with, Wikipedia close at hand. And just start reading, because that's where the game of science is played, is in the literature. Okay, so I'm forever grateful to the Inamori Foundation and also the Blavatnik School for this opportunity, and also for the people of Namibia where I worked, which were such good hosts and such good fun. And such highly cultured people. Thank you very much.
You can take a seat.
Well, thank you, Paul, for such an extraordinary tour de force of geological revolutions and insights that hadn't been possible before your great mind took them on. I guess I want to say that Paul is quite literally a giant, or more fittingly, a great bear of geology. I think this honor for him is so incredibly fitting because he's really demonstrated today that he's taken ideas perhaps that were scattered across the literature and many dismissed as perhaps crazy, and actually turned them into a reality. He's delivered a sort of narrative of actually how these extraordinary events, such as the Snowball Earth, could actually happen through painstaking, but I think notably interdisciplinary field observations. And I think the other thing that Paul has really injected into the science has been imagination and creativity. And I think that really speaks to what we're celebrating here through the Kyoto Prize. Really, Paul works on these timescales of hundreds of millions of years, which can be unimaginable to many. He's worked on plates moving around the planet in ways that are unimaginable to many. And he's worked on the extremes of climate that, again, may be unimaginable to many. But again, what I think you've heard today in this talk is just how he can transport you to the scenery, to the timescales, to the hundreds of meters thick sea ice that are covering the bone-chillingly cold but acidic ocean. And his words and his science paint a picture, but which is grounded in real truths, in the way the Earth works in a physical sense. And I think that he's really injected the field with imagination and creativity, and we can see this through the titles of his papers. He's already told us about the United Plates of America. He's talked about plates being strange bedfellows. He's talked about turning plates inside out. And I think that really creates almost a sense of fun, which we should allow ourselves to enjoy in the creativity of science. And I think he's been infectious with actually that fun, that rigidity or rigor of thought, that creativity, and that ability to have an eye for detail in a rock in high northern Canada, but combining that with big picture thinking. And as a result, he's launched an army of fantastically imaginative, creative scientists into this field and many other fields. And I think that's why it's so fitting that he's been given this award to show the advancement of excellence in humanity. Okay, so with I hope that glowing praise for Paul, who I admire enormously ever since I had the good luck to encounter him during my postdoc years, I'm going to ask a couple of questions, and then I will throw the questions open to the floor, as I'm sure they're all burning in your minds, but it gives you a chance to try and word them. So, Paul, I'm going to ask, what do you think are the key ingredients that drove the emergence of a Snowball Earth event?
Oh, I think it was undoubtedly the meeting of geology and climate physics. It was the power of combining these two very different approaches. Yeah.
And so why do you think...
Because I think the numerical simulations of the ice dynamics under the snowball conditions removed many of the objections by geologists. You see, geologists thought they knew what a snowball Earth would be like, but they didn't really. And it's very dangerous to think you know something when you don't. And so without these models, geologists wouldn't know whether the evidence they were looking at was either for or against the hypothesis. So, for example, geologists assumed that snowball ice sheets would be cold-based, they would be frozen to the ground, yet they saw evidence of meltwater. But in fact, under the snowball conditions, the lower part of the ice sheet is warmer because the accumulation rates of the ice is much, much slower, so the ice sheets have had more time to be warmed by the geothermal heat coming out of the interior of the Earth. So in fact, the Antarctic ice sheet is 10 degrees warmer in the lower part than the Greenland ice sheet, and it's because it accumulates more slowly. Another thing is geologists assume that if you cover the ocean with ice, it wouldn't feel the wind, and you need the wind to mix the ocean, and so the ocean would become stagnant. But it's completely wrong. You only need the wind in the modern ocean because the modern ocean is being heated at the top by the sun. And so the warm water's at the top and it's expanded and it's buoyant, and so that creates a stable density stratification. So you have to put mechanical energy from winds and tides to get that cold, salty bottom water back to the surface. But the snowball ocean doesn't feel the sun. It's only losing heat at the top by diffusion from the ice, through the ice. The only source of heat, it's just a trickle, but it's the only source of heat is the geothermal heat coming out of the bottom of the ocean, and so of course it drives convection. It's a very different style of convection than the modern ocean. It's mostly eddies, but nevertheless, the snowball ocean is extremely well mixed. Similarly, the atmospheric convection is very different from the modern because of the solid surface, which has almost no thermal inertia. So that explains why the Hadley cells are actually very strong in the snowball Earth, despite the fact there's very little water vapor to provide heat from precipitation, from latent heat. So how is it possible that the snowball atmosphere can get enough heat to the top of the atmosphere to be in a radiative balance with the sun? And it's because the Hadley cells get stronger the farther away they are from the equator. So they're strongest at solstice and weakest at equinox. And so we teach the wrong way by showing these two cells. The only time it looks like that is at equinox when it's weakest. At solstice, when the Hadley cells are strong, there's only one cell. Now, under the snowball condition, because the surface is solid, you get the very, very localized upwelling at the maximum insolation zone, which migrates far off the equator because of the increase in day length with latitude. And so the upwellings go out as far as 33, 35 degrees latitude. So as a result, the downwellings on the annual mean are at the equator, and that's why the snowball Earth has only one desert, and it's right at the equator. You might think that's pretty weird, because all other climates, the equator is the wettest area, and the driest area in the subtropical. The modern climate has 4 deserts, 2 subtropical deserts and 2 polar deserts. The snowball Earth only has 1 desert. So we wouldn't know any of this without numerical simulations. So it's the synergy of the meeting of geology and climate physics. And interestingly, it has a great history, because even in the 19th century, there was the same give and take between climate physics and geology. At that time, climate physics had no explanation for how the ice age could have ended, because they thought the climate could only get colder because the sun was getting dimmer. Anyway, enough for this question.
Okay, so I'm going to ask my next favorite question, and then I will open it up to the floor. But you've shown, I think, the importance of the Snowball Earth for dictating the trajectory of life after the Snowball Earth. How would life have been different, or its trajectory, had there been no snowball?
I think that life adapts to the current condition. And so if you're asking me how life would have been different under today's condition, I don't think it would have been very different. But its ancestry, its history, its evolutionary history would have been different. But, you know, whether that would have been visible to, I suspect it might not.
Okay. Are there any questions from the floor? I've already got some online, so if anybody would like to ask a question. Yes, over here. I don't know, we'll just wait a second for the microphone.
What kind of caused the end of the Snowball Earth and the return to the sort of glacial and interglacial periods we see today?
Yeah, so the theory behind Snowball Earth says it's self-reversing because of the accumulation of a greenhouse gas, carbon dioxide, because there's almost no consumption of carbon dioxide during the snowball period, but plate tectonics continues. Plate tectonics doesn't care if there's ice cover on the ocean, so you still have volcanism, you still have carbon dioxide coming into the atmosphere from subaerial volcanoes and directly into the ocean and mid-ocean ridges. So it's the buildup of carbon dioxide that eventually produces a sufficiently strong greenhouse effect to open up a narrow areas of dark water at the equator, which then absorbs sunlight, and now that ice albedo feedback is working in reverse.
I think there's a really great question online which follows on from that one, which is, why do you think the two snowball intervals, the Sturtian and Marinoan, have vastly different durations?
Yeah. Well, the warming due to the accumulation of CO2 is highly non-linear. The warming is rapid at first and then it levels off. And the primary reason for this is the logarithmic relationship between CO2 and temperature. For each increment of warming, you have to double the CO2. And when the CO2 concentration gets very large, it takes a long time to double it. That's the first reason. And then the second reason is there are feedbacks within the system, particularly involving the accumulation of dust on the surfaces. So you have dust on the surface in the ablation zone, but if you increase the dust supply, you get more meltwater, and the meltwater tends to cleanse the dust off the surface because the meltwater finds cracks, and then from the falling water and the latent heat of the water, the cracks open up to form what are called moulins. Crazy people like to climb down into these things. And so the water, that meltwater, drains through the moulins. It's a good thing it does, because that allows that 10% of the dust that is actually organic matter to get buried, and that's what allows the oxygen in the atmosphere to be retained, because otherwise the volcanism would rapidly eliminate all the oxygen in the atmosphere. So there has to be some carbon burial, and that's from this cryoconite, this ice dust impregnated with this heavily pigmented, extracellular cyanobacterial product that gets buried. So there's a feedback, because you more dust, more meltwater, more cleansing. And if the rate of the removal of the dust equals the dust input, it could stay sort of perpetually at a given albedo level. So there may be a reason why they're so different in age, and you would like to think that that reason would be the younger one was shorter because the older snowball had occurred. Okay, that would be, that would be the simplest and most cleanest explanation. But so far, we haven't come up with a good explanation, and I'm not completely convinced that it's a really important problem, other than the fact that there are some geochemical differences as well that could be related.
Okay. Any other questions from the floor? I have a whole ton in my, in my book that I was scribbling down. Okay, there's one right at the back.
Hi, I'm just really curious. Do you think that we will ever know about the sprawling life that was lost to Snowball Earth, considering our current geological methods? Thank you.
Yes, because we have the fossil record. And the fossil record is what gives us a degree of access to extinct lineages which we cannot study with the molecular methods, although we can from molecular fossils. Okay, so by fossils, I mean both physical fossils and also molecular fossils. And so, for example, there are steranes, which are compounds produced by eukaryotes, but they're steranes that are not produced by any modern eukaryotes, and yet they are the dominant steranes in pre-cryogenian molecular fossil assemblages. And so I think there's a good possibility that those steranes were produced by, eukaryotic algal lineages, because these are in, large abundance, that did not survive the Snowball Earth. And so they're not, directly ancestral to modern organisms.
Oh, yes, here in the front row. Sorry, if you just wait a second for the microphone, and then those online can...
Or I could repeat the question.
Yeah, okay, that would be an alternative. Nearly there.
There is much in your thinking that is in common with the thinking of James Lovelock and Gaia theory. Is there anything useful in that way of looking at things?
Yes, I think that the CO2 geothermostat is essentially an inorganic, Lovelock, Gaia. Yes, I think it's very Gaian, but it's not a form of Gaia that's primarily driven by the biosphere, although it doesn't negate that there may have been biospheric factors as well. But it's due to the temperature dependence of silicate weathering, which is the main sink for carbon dioxide.
Looking forward, are there any predictions that you might like to make about this period of climatic instability that we seem to be going into?
Well, what we know from the simulations and also from first principles is that you're most susceptible to a snowball Earth when the ocean is cold, because the ocean is the main, thermal inertia in the climate system. It's by far the largest heat reservoir that we have. So it's much easier to make a snowball Earth when the ocean is close to the freezing point to begin with. And of course, we have a very cold ocean by geologic standards today. 55 million years ago, the ocean was 12 or 14 degrees C. But the mean ocean temperature today is somewhere between 1.5 and 2 degrees. And the freezing point is -2. So we're actually fairly close. So we're actually quite vulnerable today. And so simulations suggest that a Cretaceous Tertiary, the impact that exterminated the dinosaurs, if that hit the Earth today, there'd be about a 50-50 chance of a snowball Earth occurring. The reason is because you put up a lot of dust and it blocks sunlight, but it pretty much rains out within a decade or so. So you have to do, you have to work quickly because it's a fairly short-lived perturbation as far as the climate system is concerned. But yeah, I think the main vulnerability, see, the paradox of snowball causation and the causal factor has still not really been settled upon. There are many contributors, but we don't know exactly how it worked. But the puzzle about it is that it's a rare event. I mean, it only has occurred on average once every billion years, because there's not more than 3 in the last 3 billion years. There's 2 that we know of and a fair possibility for a third. So it's a rare event. So you'd like to think that the cause was either a rare event or a rare combination of more common events. But the problem is there are 2 of them in succession. And that suggested that there was some vulnerability or susceptibility at that time that made it much more probable than average. Otherwise, it was just a fluke, which is also possible. There's this small number of statistics. I like to joke that I got out of supercontinents because n equals 4, and I ended up in Snowball Earth where n equals 3. This is not progress.
Okay, we have another question over to the right here.
Thank you very much for your talk. There's been a lot of research lately that manganese nodules on the ocean floor are a source of oxygen. Do you think they could have arisen in previous eras and also contributed to climatic events?
Yes. I settled on some objection I had to that idea, and I'm trying to remember what it was. Well, I guess under the snowball conditions, I'm not sure there would be manganese nodules on the ocean floor, because the deep ocean was anoxic at that time. So I guess that may have been the reason why I thought that this is not probably an important factor in making oxygen during the Snowball Earth.
This chap in the pink, am I missing anybody? I'm noticing that we've only had questions from men. If any females would like to step up, or those alternatives, then please do. But otherwise, we'll go to...
Do you have any ideas as to why it is that more recent glacial periods didn't result in a snowball Earth, while those of the Proterozoic did?
Yeah, some people think we came very close, around 315 million years ago. Yeah, I don't really, we have a lot of bioturbation now, which makes it more difficult to bury carbon, but that's only one sink for carbon. I don't really have a good explanation, other than just the fact that it's a rare event, but yeah. And I guess I'm crippled because we don't have a good, well-tested explanation for why they occurred in the Cryogenian. So until we know that, it's really difficult to come up with a very convincing, or even to spend a lot of time thinking about a convincing explanation for why it did not occur, which is a more difficult problem, in the last 500 million years. So.
Okay, I'm going to take Chair's prerogative here, and I'm going to ask this question that field geology may be seen as a very traditional way of understanding Earth history, and also sort of makes geology perhaps seem a very traditional discipline. How do you see the role of field geology playing out for the general discipline of geology into the future?
Well, I think it should be recognized that we have much better tools now. And the main tool that we have is accurate geochronology. And virtually all geological models that concern history make predictions about the timing and the duration of things. And so what I learned from working with Sam Bowring, one of the pioneers in uranium-led geochronology, who worked with me up in the Watmay origin, is that I like to say he converted my work from competitive drafting to real science, because he gave us the tools through which we could test tectonic models. And it meant that our thinking was changing on a time scale of weeks to months instead of years to decades. And so much of the field geology that has been done needs to be redone with these modern tools, particularly the geochronological tools that we have now, and which sadly are not well distributed around the world. There's not a single uranium-led geochronology lab in all of Africa, for example, nor in South China, although 2 are planned. They have a very serious lead contamination problem there.
That's fantastic, Paul. So with that, I would like to thank all of the audience for coming and giving us such vibrant questions. I'd like to thank Paul for giving us just such an extraordinary and expansive and mind-bending talk about the way the Earth actually works. And I should also thank the Inamori Foundation for being able to, for us to be able to enjoy this event and to hear from Paul and to partake of the celebrations. So with that, thank you very much.
Well, thank you, Raj.
Thanks, Paul.